Hello, and a very warm welcome to you. Today, we're going to embark on a journey into the very heart of the electricity that powers our world. Have you ever plugged something into a wall socket and wondered what's actually happening? What kind of power is flowing through that cord? The answer is beautifully captured in this single image, the AC waveform. Now, this diagram might look a bit technical at first glance, with its curves, letters, and symbols. But my goal today is to walk you through it, piece by piece, in the simplest terms possible. We're going to demystify everything you see here. By the end of our time together, you won't just see lines on a screen, you'll understand the elegant, rhythmic dance of energy that this graph represents. So, let's begin. First, let's look at the title itself, AC waveform. The AC stands for alternating current. This is the most crucial concept to grasp. Imagine a river. If the river always flows in one direction, from the mountains down to the sea, we could call that direct flow. In electricity, this is called direct current, or DC. It's the type of power you get from a battery. It's steady and flows in a single, unwavering direction. But alternating current, or AC, is different. Imagine our river, but instead of a steady flow, the water surges forward for a moment, then slows down, stops, and then surges backward, before stopping and surging forward again. It's constantly alternating its direction of flow. That's exactly what AC electricity does, and this waveform is a visual graph of that very process. It's a story of energy that's always in motion, always changing. To understand any story, we need to understand its setting. For a graph, the setting is its axis. Let's start with the vertical axis, the one pointing upwards. This is labeled voltage or current. These are two fundamental ideas in electricity, so let's use a simple analogy, a water hose. Voltage is like the water pressure. It's the push or the force that makes the electricity want to move. A higher voltage means a stronger push. Current is like the flow of water itself. It's the amount of electricity that's actually moving through the wire. So, this vertical axis tells us the strength of the push, voltage, or the amount of flow, current, at any given moment. The higher up the line goes, the stronger the positive push. The lower down it goes, the stronger the push in the opposite, negative direction. Now, for the horizontal axis, the one going from left to right. This one is labeled time. This is perhaps the easiest part to understand. As we move from left to right along this line, we are simply moving forward in time, watching how the voltage and current change. The point at the far left, labeled O4 origin, is our starting point, time 0. Okay, with our setting established, let's follow the plot of our story. Starting at the origin, O, where time is 0 and voltage is 0, watch the white line. It begins to curve upwards, moving away from the horizontal timeline into the positive territory. This entire first arch of the wave, the part that exists above the time axis, is called the positive half cycle. It's called positive because every value of voltage or current in this section is a positive number. During this entire interval of time, the electricity is flowing in one primary, forward direction. It starts from nothing, grows stronger and stronger, and then begins to weaken again. The wave rises until it reaches its highest point, the very summit of this first hill. This peak is incredibly important. It's labeled here as Vm or M. Let's decode that. The V stands for voltage, and the I stands for current, as we just discussed. The little subscript m is shorthand for maximum. So, Vm means the maximum voltage, and M means the maximum current. This value is also known as the amplitude of the wave. It represents the absolute maximum strength or push that the AC signal achieves in its positive direction. After reaching this peak, the momentum changes. The signal's strength begins to decrease, and the wave curves back down towards the time axis. The wave continues its downward journey and, right here, it crosses the time axis again. This specific point in time is labeled t divided by 2. This means 1/2 of the time period. We'll define the full time period t in just a moment, but for now, understand that at this halfway point, the positive half of the journey is officially over. The voltage and current have momentarily dropped back to 0. But the story doesn't end here. This is where the alternating part truly comes to life. Instead of stopping, the wave continues its path, diving below the time axis into the negative region. This entire second arch of the wave is called the negative half cycle. Now, the word negative here can be misleading. It doesn't mean bad or a lack of power. It simply means the direction has reversed. Going back to our water hose analogy, in the positive half cycle, the water was being pushed out of the hose. In the negative half cycle, the pump has reversed, and now it's pulling the water back in. The flow is just as strong, but it's happening in the complete opposite direction. This constant back and forth, positive then negative flow is the essence of alternating current. Just as the positive cycle had a peak, the negative cycle has a bottommost point, or a trough. This is labeled negative Vm or negative M. This is the negative peak value. Notice the minus sign. It tells us the direction is negative. The Vm or M part tells us the strength or magnitude. And critically, this strength is exactly the same as the positive peak. So, if the peak positive voltage was, for example, plus 120 volts, the peak negative voltage would be minus 120 volts. The push is just as strong, but in the opposite direction. After hitting this negative peak, the signal's strength in the reverse direction begins to weaken, and the wave starts to curve back up towards zero. The wave continues its upward journey and finally returns to the zero line at the point in time labeled t. At this exact moment, the waveform has completed one full, beautiful, symmetrical cycle. It has gone through one complete positive half cycle and one complete negative half cycle. This total duration, the time it takes for the wave to complete one full cycle before it starts repeating itself, is called the time period, represented by the capital letter T. This process happens incredibly fast. In North America, the standard frequency for AC power is 60 Hz. A Hertz just means cycles per second. So, 60 Hz means that this entire waveform, from 0, up to a positive peak, down through 0 to a negative peak, and back to 0 happens 60 times every single second. In Europe and many other parts of the world, it's 50 Hz, or 50 times per second. It's a relentless, high-speed oscillation. Finally, let's look at the equations in the box. I know math can sometimes seem daunting, but these formulas are actually the language that perfectly describes the beautiful wave we've been admiring. Let's translate them. The first is V of t equals Vm sine omega t. V of t is a way of saying the instantaneous voltage. It means, if you tell me a specific time t, I can tell you the exact voltage V at that precise moment. Vm is our old friend, the maximum or peak voltage. This number determines the height of our wave. The term sine omega t is the mathematical engine that creates this shape. Sin is the sine function from trigonometry. Its one job is to produce this smooth, repeating, up and down wave pattern. The part in the parenthesis, omega t, connects the wave shape to the passage of time. So, this whole equation is a recipe. It says, to find the voltage at any time, just take the peak voltage and multiply it by the value of the sine function at that time. The second equation, I of t equals m sine omega t, is the exact same story, but for the current. It's the recipe for finding the instantaneous current at any moment in time. So, there we have it. Let's put it all together one last time. This is an AC waveform, a picture of alternating current, where the flow of energy constantly reverses. The vertical axis shows its voltage or current strength, while the horizontal axis tracks the passage of time. It begins a cycle at 0, rises through a positive half cycle to a maximum peak, falls back through 0, dives into a negative half cycle to a negative peak, and returns to 0 to complete its time period. This entire, elegant dance is perfectly described by the sine wave equations. This single cycle is the fundamental heartbeat of the electrical grid that powers our homes, our cities, and our modern lives. Understanding it is the first giant leap into understanding the fascinating world of electricity. I truly hope this in-depth explanation has made this concept clearer for you. It's a beautiful piece of physics, and now you know how to read its story. Thank you so much for watching.